All right, we are at section 14.3, the speed of sound. Let's go to the PowerPoint. And the speed of sound is dependent on the speed of sound in a fluid, I should say, is dependent on the bulk modulus divided by the fluid density. So you can see that the bulk modulus, if you hopefully you had it earlier in the semester when you studied Young's modulus, bulk modulus, shear modulus. Bulk modulus is the change in volume for a given change in pressure. So when you increase the pressure, the volume decreases. So that decrease in volume is a negative. So the fact that the bulk modulus is a minus P over a minus delta P over delta V over V naught, the original V, V is always positive. So you have a negative times a negative volume, you end up with a positive. So it's the bulk modulus over the density of the fluid. And that's always true. We had a velocity for a string, and it's always the velocity is related to the square root of the elastic property over the inertial property. In other words, for the string, it was force divided by the mass. So a transverse wave on a string is the velocity is the square root of the force divided by the mass, the linear mass density mu. And for longitudinal wave in a rod, it's Young's modulus over the density of the linear density of the rod. And here's some typical speeds of sound. Typically, in solids, the speed of sound in solids is higher than the speed of sound in liquids, and that's higher than the speed of sound in gases. Now you can see that the speed of sound in hydrogen and helium are pretty high. In air at 0 degrees, air at 100 degrees, and oxygen, they're all about in the 300 to 400 range. But helium, if you've ever seen, where someone inhales helium, which I'm not recommending, it's better to have surgical grade helium than just helium out of balloon. I mean, people do it all the time, but that's why your voice sounds higher, because the speed of sound is so much faster in helium. The speed of sound is very fast in liquids, water, methyl alcohol, and seawater. And then it's very fast in metals. You can see it's very fast in aluminum, not so fast in lead, and less and so in synthetic rubber. Now the speed of sound in air is given by 331 meters per second times the square root of T over 273 Kelvin. So the temperature that you have to put in there, it has to be the Kelvin temperature. And you're going to get a different formula in your lab book. You're going to get a different formula when we do the air resonance. And you'll see if you were to plot them. As a matter of fact, I may assign that as an extra point. Give me two plots with this formula and the other formula given in the lab book. I'll have to give you that formula. I haven't posted the experiment yet. So for T equal 293 Kelvin, about 20 degrees Celsius, that's room temperature. The velocity is equal to 331 meters per second times the square root of 293 over 273, and you end up with 343 meters per second. So when we do the speed of the air column resonance, we're going to discover it's about anywhere from 340 to 345 meters per second. Okay, and that's it for this small section. We'll go on to 14.4, the energy and intensity of sound waves in the next section.